Okay, so let me begin. I don't know Jacob. In fact, he's coming, but maybe at some point he'll come. So let me just to recall some notation from the last time. So I'm going to take simple Lie algebra or complex numbers. We fix a Borel and a Cartan. And now I'm going to fix two integers as we did last time. So S will be number of markings and C will be central charge. These are both positive integers. And now by a S-pointed curve, we mean a reduced projective curve sigma, not necessarily connected with at most nodal singularity, and with S marked points P, P1 through PS, which are distinct and smooth. Moreover, we assume that each irreducible component of sigma contains at least one PI. So I just want to, we just want to ensure that sigma minus this P whole set is an affine variety, because we will need functions there. Okay, so continuing with that, affine Lie algebra. So this is the definition. Of course, I don't need to recall that, but in any case, I will put it down. So this bracket is the standard bracket here, but you put the central charge, central component here. So this is the invariant bilinear form on the Lie algebra, and it's normalized theta check is 2, and then the space of dual conformal block is by definition, we take h lambda and we divide by this. So this is the covariant space with respect to this action, where lambda is lambda 1 through lambda s attached to P. So P1 is attached to lambda 1, or lambda 1 is attached to P1, and PS is lambda s is attached to PS. And I take each lambda I in DC, which is dominant weight for the finite Lie algebra G, but with this additional condition, lambda theta check should be at most C. And actually, I will come to that in a minute. That's what I'm going to discuss now. And this lambda is just the tensor product of these things. Now, so we talked about various theorems last time. So one is the invariance under local parameters. So this requires the choice of local parameter. In any case, I'm going to explain that. And then finite dimensionality of this space, and then propagation theorem and factorization theorem. So that's the aim today, to at least give enough indication of the proof of these things. Okay, so Jacob, I just started actually. So actually, I'm just recalling some notation from last time, which probably you don't need to recall. So, and then I was just saying this thing. So, so that's what I'm going to do. So I will start with a very a brief discussion of representation of affine Lie algebra. So that's where I will begin. So representation of G hat. So the central charge, central charge of a representation just means the action of C. Okay, so so my main interest is, more or less, my main interest is in the integrable highest weight modules for G hat. So that will be the subject of main interest. So before that, I need to define this generalized Verma module. So, so to define this, I need two things. So I need one V in representation of G. So I mean, right now I'm just taking any representation of the Lie algebra G, and I am taking one C, which is a complex number. So that's going to the central charge. And then I'm going to define this generalized Verma module, and this is depends upon V and C, and this is just the induced representation from UG hat UG tensor and then I'm going to write V here, and I have to explain how does this act. Okay, so this is G hat, and this is the subalgebra. So this is the standard maximal parahoric subalgebra. So only thing I need to tell you, how does this act on V? So V is a G module. So G tensor CT, of course, has evaluation X tensor F going to X tensor F0. And so that's how this portion acts on V. And the C's, so this is a capital C. Actually, my small c and capital C are a bit difficult to distinguish. So this capital C is acting on V by this fixed small scalar C. So then I will use it. So this is what is called the generalized Verma module. So generally, Verma module would have meant this one, but for the Borel subalgebra. So that would have been the Verma module. Okay. So now I want to talk about integrable. So classification of integrable.
Sorry, can I ask?
Oh, of course. Just give me one minute. Just give me 1 minute. I will be with you. Yes, what's the question?
Do you talk of a highest weight condition for this Verma module?
It's already by definition it's highest weight.
Okay.
It's by definition.
The fact that you pick the Borel or
if you take the highest weight of the representative of the real Verma, then it will be the way you think. Also, highest weight representative.
okay.
So you see, right? I mean, right now I'm taking V completely arbitrary, but I'm going to take finite dimensional irreducible representation for
You haven't done that.
So then it will become as Pierre said. So that will be okay. So right. So I am going to define. So take lambda in DC. So where I define DC somewhere. Did I define? I thought it's here. So DC is dominant integral weights for the finite G with this additional condition. So now let's take lambda in DC. So in particular, it's a dominant weight for G. So this gives me a V lambda irreducible representation of G with highest weight lambda. And of course, it's finite dimensional because I'm taking a dominant weight. So now I will run this construction M hat V lambda, and I am going to take this C now. So which satisfies this condition. Okay, so first of all, it's integral and it satisfies this condition. So I take that. And now I'm going to quotient out by one element, and that is so I'm going to write quotient out by UG hat module generated by one single element. Let me write it and then I will explain the notation. So this I'm going to denote by X. So let me, yeah, unfortunately, my capital C and small c, they look almost the same, sorry. So I take this generalized Verma module, and I have to explain what is this. So x theta is a root vector in the highest root space, and x theta T inverse, of course, means, I mean, not of course, but it means. So I will often make this abbreviation that I will write x theta T inverse, which will mean x theta tensor T inverse. And then I am raising it to power C minus lambda theta check plus 1. Okay. Now you will see why this C is bigger than or equal to lambda theta check. So that becomes a positive integer. And then what is V plus? So V plus is the highest weight vector here. So in V lambda. So V plus is highest weight vector in V lambda. So I mean, really I should. So V plus actually, I mean, I'm being a little bit. So I could just write 1 tensor V plus, just V plus is 1 tensor V plus. So that's the highest weight vector. So I quotient by that.
Has the effect that for some particular SL2 survival?
Yes, that's right.
Something like that.
Exactly. That's exactly right. Yeah, absolutely. So, right. So in fact, let me say that. So the G hat is of rank L plus 1, L being the rank of the finite G. And this has L plus 1 like standard SL2, maybe I could call that. So G already has standard SL2 passing through the simple root vectors. Now G hat has one other SL2, and that passes through exactly this. So x theta T inverse, and then I will take x minus theta T, and then C minus theta check. I may not have written exactly the standard basis of SL2XYH, but it's the span of this SL2. So this works as the positive part, this works as the negative part, and XY, I mean, we just have to calculate. Maybe there is some factor there. Maybe there is not. Yeah. So you see, V lambda already is integrable for the finite G.
Sorry.
Yes.
Okay, by integrable, you mean there's an action of the group.
That's right.
Okay.
I mean, okay, that's right. Even though right now, to be very technically correct, I have not introduced the group so far,
yeah.
But there is, yeah, so integrable. Let's just understand that integrable means that corresponding group integrates to a, I mean, this representation is really integrates to a representation of the group.
Yeah. So when you say integrable highest weight module, you mean it integrates just for G or for G double brackets T, or which?
No. So it integrates for G hat. So see, so G hat is this affine algebra, and there is a corresponding group, which so far I have not talked about, but in any case, so loop group, so it's a central actually.
Okay, you want to integrate to the, okay.
Exactly. So it's the central extension of the loop group.
Okay.
And this representation integrates, right? But actually, right now, I don't even have to say, I mean, I can give a more formal definition, which does not require the group right now. And it just means that, so I have given you SL2 theta, and there are already SL2 in the finite G. So let's take those L plus 1 SL2. Are you with me?
Yeah, one thing I can tell, just for the algebra itself, you have a number of standard SL2 for each root E alpha, E minus alpha and something. Now you can take E alpha times T at T power n, E minus alpha at T power T minus n, and the bracket will be something. And this is an SL2. And that is one particular of those SL2, but you also want all of them to be integrable, but as understand this particular one is enough.
Yeah. So the point is that this representation decomposes as finite dimensional representations of all these SL2. And that's the difference. So if it decomposes a direct sum of finite dimensional representation, you can integrate as a representation of the corresponding group SL2.
Okay, but the reason we're talking about that is because of some statement that you haven't told us that implies integrability for the full.
Right.
Is that right?
That's right.
Okay.
That is right. So okay. So let's right now take this definition by integrability. We just mean that under all the SL2s, so I will just call it SL2 alpha I from 1 to L, and alpha I are simple roots of G, okay, and SL2. So let's take L plus 1 these SL2s, and our representation decomposes as a direct sum of finite dimensional representation, which is saying that it integrates to a representation of the corresponding group SL2. I will just call them integrable, okay? Just a tentative definition, but it's equivalent to saying exactly what you said.
Because these guys generate.
Exactly, that's right, exactly. They generate, exactly, that's right. So they generate the Lie algebra, and the corresponding SL2 group will generate our group also. Anyway, we'll come to that group part a little bit later. So let's see what was I saying. Now, right, so HC lambda. So theorem that HC lambda is an integrable highest weight G hat module with central charge C. I mean, it does require a little bit of proof, but in any case, I'm not going to give the proof. Right. I mean, highest weight is clear from the definition because this V lambda is highest weight module for the finite G, and then we are just taking UG height with that. So highest weight part is completely trivial, but integrability does require a little bit of proof. But I will not give.
Sorry, what is the, just say in words, what is the definition of highest weight?
So high, okay, right. So, okay, let me give it.
You could just say it in words.
Okay, so it just means that there is a vector there in that module such that it's annihilated by the Borel subalgebra. Actually, no. That line is fixed by the Borel subalgebra, and that line generates the whole representation as a G hat module.
But by the Borel subalgebra of G hat, what do we mean?
Right. Okay. Right. Okay. Yes. So quick question. So G hat is by definition G tensor T C.
Okay. Plus B.
Plus
yeah, B. Okay.
Plus.
Okay.
Right. Exactly. Good. That's right. That's right. Exactly. So that is the definition of highest weight module. Is it clear to everyone? Right. So theorem is that this is an integrable highest weight G hat module with central charge C, and actually I should say it is non-zero. I mean, yes.
Sorry, the statement is that it is already highest weight, but after you take this quotient,
That's right. Exactly.
it becomes integrable.
That's right.
That's when it's
That's the main part of exactly. You are absolutely right. Quotient of highest weight is highest weight, but so that's trivial. but it being integrable requires a little bit of proof. It's not very, very, very difficult, but it requires a little bit of proof.
So if those L+1 is L2, then it gives you an L+1 element in a Veil group.
Yes.
So you go from those as L2 to all reasonable as L2.
Okay, so maybe you have some other proof in mind. So this proof, at least which I have in my mind, does not require Veil group. So there is another proof which does not require Veil group. Actually, maybe at the end, maybe I will state a lemma, a general lemma about Lie algebra representation. And actually, it's a very useful lemma. I found it. So maybe I will write it, but let me continue here. So, right, and then theorem, and this is the main theorem for the inclusion theory, that so this DC to integrable highest weight G hat modules with central charge C are in bijective correspondence with this, and lambda goes to this H lambda. And I will write this C sometimes, but because I'm going to fix C once and for all, so I might just drop it. So irreducible. Actually, it becomes automatically irreducible. So in
Highest weight.
Oh, it's highest weight.
yeah, so it's highest weight and integrable. That makes it irreducible, right? But you need integrability, otherwise, of course, it's not true. So that's right. That's right. So it automatically becomes irreducible. Yeah.
Wait, so are there restrictions on the central charge?
Yes. No, there's no restriction on central charge. So I am fixing a positive integer C. That's the only restriction.
Okay, it's an integer.
Okay. Right, that's right. Oh, definitely. Oh, I mean, I should say definitely, but yes, that's right. In fact, before you came, I wrote that I'm going to somewhere. Yeah, somewhere. We fixed two integers, right? Yeah. Anyway, so yeah. So we only fix positive integers. Actually, even C equals 0 makes perfectly good sense, but then the representation becomes one-dimensional representation, so we don't worry about that.
And morality is an integer because this central C is the Lie algebra of a TM group, and so you have a character of a TM.
Right. Yes. Yes. Right. Okay. Anybody, any questions so far? Now, this theorem does require, of course, proof, and little bit, slightly, it's not completely trivial, but not too hard. Okay, so the next thing I'm going to do, which is on our agenda, that invariance under local parameter of this space of conformal blocks. So that's what I'm going to prove. Okay, so
So I have a question.
of course,
How can I picture, say, HC of 0? Like, okay, I understand what the generalized Verma module looks like,
yes.
but I have no real sense how much of it you've killed. So what kind of mental picture shall I have?
Okay. That's a hard question. maybe some of us can answer. But there is a character formula.
Okay.
Just like the wild character formula, there is a very precise character formula, and that is called wild cast character formula. And in fact, it looks exactly like the standard character formula. And the character formula, let me write it. So the character of HC lambda So now character, we are doing it with respect to the cartan of the G hat.
Yeah.
And G hat has cartan, the usual cartan for the finite one, plus CC. Actually, we also generally included derivation in the theory, but I am not using that. So I will write down this character, and this is epsilon W. I will explain the notation. A W
Character formula reflecting that the integrable module has a resolution by Verma modules.
absolutely.
And now you have all translates by the affine Weil group.
That's right.
Parameter period.
Exactly. So now we take the affine Weil group, and lambda is this rate, and W star lambda is the usual W, lambda plus rho minus rho.
Rho is the usual rho.
No. Rho is the affine rho.
What is that?
Okay, so yeah, correct. So affine rho. So let me put it like that. For the affine things, I put a hat. So rho hat is an element in H star such that rho hat on alpha I check is 1 for all alpha I check from 0 to n. Okay, so there are finite alpha I check, that's usual one, but there is also an alpha 0 check, and alpha 0 check is okay, alpha 0 check, I think is this one.
So the answer to Akshay's question is, if you want to present this thing by generators and relations, you take the highest weight vector in the Verma module, and then you say it has to be killed by certain powers.
Exactly. That's right. Exactly. But you see, I mean, that is correct what you're saying, but it becomes a bit complicated in the sense that if you have to write this module very explicitly, it becomes complicated as to, I mean, of course, you have a character formula, but I mean, just like, let's even take quite affine G, let's take finite dimensional G. And suppose I give you a finite dimensional representation. Of course, there is a very similar description of that in terms of the Verma module. But I don't know, I mean, if I have to calculate from the definition, I don't think that I will succeed in general, right?
So the resolution by Verma module,
Yes.
you start with the
Correct.
one you said, and then you have n plus one of them.
That's right, exactly.
Do it
Exactly. So the BGG resolution, and that's what it's called, BGG resolution, it's exactly like in the finite case, except that you change your Y group with the affine Y group, and you change the rho with the rho hat, this one. And yes.
How did, so then I'm very happy with that answer.
Yeah.
Then how do you somehow get by killing only one thing in this?
You see, because I took the generalized Verma module, I already killed here.
Oh, I see. Good.
See, I already killed.
Exactly.
I already killed the garbage from the finite.
Okay.
So to say.
Okay, that's very good.
Yes, right. Are you happy, Jacob? Are you happy? Yeah, okay. Very well. Right. So invariance and the change of local parameter for this V sigma P lambda. So see what we did in the definition of this V sigma P lambda, which is here. This is here, is that, so let me just again a little bit write it. So this G sigma minus P acts on H lambda 1, H lambda S by, so we take X tensor the function here, and V1 tensor Vs, and this will be V1. In the ith factor, I take X tensor F, and I take a local parameter, and I take the Laurent series expansion of F at Pi. That's what I'm doing. And this. So this involves a choice of a local parameter at each of the Pi. And now what I'm going to prove that it does not depend upon the choice of the local parameter. This is space. So, right. So let's first see let's fix one local parameter.
What's the it that doesn't change the isomorphism class of the representation?
That's right. That's right. And in fact, even canonically, so even I don't need a scalar factor there. But in any case, since I'm going to use a scalar factor in the end, I will not bother too much, but I will just make a small remark that this isomorphism does not even depend upon the choice of the scalar. Okay, so that's right. So if I fix one local parameter, so then any other local parameter is going to be given by, so let me, yeah, is going to be given by a power series. So I'm just focusing my attention on one of the PIs, and I'll just call it P like. So omega TCT with two properties, omega 0 should be 0, and omega prime 0 should be non-zero. So if I fix one local parameter, any other local parameter is given like that. Okay. Now this gives us an automorphism of CT that is F going to F composed with omega. So this gives me an automorphism of the field. And in turn, this gives me an isomorphism of our automorphism of G tensor C. So G hat. And under this automorphism, I will take C to C. Rest is given by this automorphism. I just take a G tensor. So just identity here, and here I put this automorphism. So this gives me a Lie algebra automorphism of this one. Now let's.
So you use that residue is invariant.
Yes, exactly. That's absolutely right. So the residue is invariant under this exactly, of course, absolutely. Right. So let's observe that this thing, G tensor CT, goes to itself. So G tensor CT goes to itself. And now what we are going to do, so we have an original H lambda. I will drop the C here. So we have an original H lambda, and I will use this automorphism, and let's call it something. Right. Just to be sure, I'm just going to call this automorphism phi omega. Yes, that's right. And so H lambda will, right. So twist H lambda by phi omega. So phi omega is a Lie algebra automorphism. So I'm just going to twist this H lambda by phi omega. And just to distinguish, I will call this H lambda twisted by phi omega as H lambda prime, just to distinguish. Okay, so lemma. So there is a linear isomorphism phi omega lambda from H lambda, linear isomorphism, which has the property phi omega lambda X and V is phi omega X and phi omega lambda. So right now I'm just calling that this is a linear isomorphism. Yes. Okay, and that's pretty clear, I think, right? Because I'm just using right, so is that clear? So phi omega lambda, I'm saying that this is a linear isomorphism satisfying this property. Is that clear?
What I understand is that first for this Generalized Verma module, it's clear, it did not change.
Yes, that's right. That's
But
right.
then you have to know that what you define by
Yes.
makes the same.
Sorry. Okay, sorry. No, this is slightly, yeah, right. Okay, right. No, this requires some proof, which let me say that. Yes, okay, no, yeah, no, it does require some proof.
Can I ask
Of course.
a broader thing?
Of course.
Is there a version of this with the Virasoro algebra?
Oops.
That is to say,
Certainly.
okay, this extends to some semi-direct product.
Yes, that's right.
Okay.
I would definitely think that.
Okay.
That's right. Yes.
Won't you need it to have the connection?
Wait, doesn't that fail at the critical level, or is the critical level not?
There's no critical level.
It's not integral. Is that the?
No. See, the critical level is minus the dual Coxeter number. That's the critical level. So critical level is minus the dual Coxeter number, which is negative number. I'm always taking positive number. So the critical level does not interfere here. Yes. Sorry, Venkatesh.
So that's all. Okay.
Yeah,
So
yeah.
it's a special case. There's a stronger result about.
Yes,
So to
that's
speak.
right. That's
We're just thinking about some part of the Virasoro algebra here.
yeah, right.
Using the group instead of
Using the group, yeah.
Right, exactly. Yes, right. Okay, so let me indicate the proof. Sorry, So let's analyze this H lambda prime. So H lambda prime is a representation also of G hat, and as a vector space is same as H lambda as a vector space. So this is H lambda as a vector space. Now H lambda has a fixed line which is fixed under the Borel of G hat, a unique fixed line. Now let's observe that that line remains fixed under G hat. It does not change that line because C power series T goes to itself. It does not change that line. So in particular, so this was the line V plus here. The same line remains which is the highest weight space. Now, so this is okay. So this is the highest weight module, and also the cartan is not changed because cartan was cartan I've written here. This is the Cartan, right? I mean, I'm not taking D, so this one. So the Cartan remains the same. See, because in the finite part, nothing is happening. Yeah. In the finite part, nothing is happening. So the Cartan remains the same. So the action of Cartan here is same by the action of Cartan here. And the Cartan acts by the weight lambda here. And the central charge is C. So the action of Cartan breaks into two parts, action with respect to the finite H and action with respect to the central charge. And the central charge C is going to be C. So as Pierre pointed out, that residue does not change under this automorphism. So that means that H lambda prime is also a highest weight module with the same highest weight. Right? So H lambda prime is also a highest weight module with the same highest weight, because that generates this one. I mean, this line generates the whole thing here. Okay, so the only thing we have to prove that it is integrable. That's the only thing we need to prove, that this is integrable. Now, okay, so right, that's the only thing we have to prove, that right.
As you did not clearly define integrable, this is a little troublesome.
Right, that's right. Okay, so okay, right. So yes, you are absolutely right. So the point is that integrable highest weight module is irreducible. And any highest weight module with highest weight which is integer, I mean, which is highest weight which is satisfies in DC, there is only one module with that because of the classification. So I am not going to use the definition of the integrability. I'm just going to use the fact that a highest weight module, which is irreducible and has highest weight of the right form, is going to be integrable automatically. Does that make sense? So any highest weight module with highest weight lambda in DC and which is irreducible will be integrable. Okay, so now we have already proved that it's highest weight, and we know that its highest weight is in DC. So only thing we have to prove that it's irreducible, but that's clear, right? Because I am pulling the G hat action via some automorphism of G hat. So of course it will remain irreducible. So this module is actually a G hat module, same as H lambda. Okay, now you see, so the only ambiguity may be that the highest weight line I chose, so there is an ambiguity of scalar. But you see, again, I can take a highest weight vector here, and the vector space is the same. I can choose the same highest weight. I mean, I'm not going to fuss about this because in any case, later I am going to lose my scalar in any case. I will not fuss too much about that. But those of you who...
In your definition of Generalized Verma, then it's clear Generalized Verma did not change, and you take the only...
Exactly. That's right. Exactly. So that gives, and once we have this, then this lemma follows. I mean, it's just saying that this is a G module. And once we have that, then this is space. Right. So the quotient of this will be identical if I change the parameter, local parameter.
But the input is that this construction gives something irreducible, which is not obvious, right?
Absolutely. So yeah, so you know that is the problem, because right. right. There are some things which I am not really proving, but you are absolutely right. So what one proves, so the integrability of this is not difficult to prove under the definition which I gave you, I told you. But once you have integrability, what one proves that any integrable highest weight module is irreducible, which is a theorem. And once you have that theorem, then I can revert the rule that any highest weight irreducible module with the correct highest weight, means in DC, will become integrable. So I am reverting the rule. Does that make it clear? Okay.
Sorry, Shrawan, can I just ask the?
Of course.
So by local parameter,
Yeah.
change of local parameter, you really mean this omega of t, which changes, is the parameter is t?
Right.
Or, yes?
That's right.
Okay, and so basically
So,
change
no, no.
t to, oh, yeah,
So I started with some local parameter t,
t, right.
and now I'm changing the local parameter to omega t.
Omega of t, which is which vanishes when t vanishes, and it
Correct.
yeah.
Exactly.
So it's a reparameterization of t.
Locally, that's right.
Locally.
That's right. That's right.
Okay.
Does that?
Yeah.
Yeah.
I think.
Okay. Anybody, any questions? Yes.
And is the idea of the proof of the statement you made that integrability plus highest weight implies irreducibility?
Right.
Use the integrability to say that you can reflect, if you take a sub-representation that you want to prove doesn't exist, and
Right.
you want to show that it contains the highest weight vector, and so you
Right. Exactly.
try to go down and then use
Yeah.
reflections to go back up.
Right. Right. Okay. So see what happens. I will tell you that. So to prove that an integrable highest weight module is irreducible, so the way one proves, actually, even in the finite dimensional case, let's say at least I can tell you one proof. Maybe you people know other proof, but I can tell you one proof, even in the finite dimensional case. So you construct an integrable representation, let's say finite dimensional representation, which is quotient of Verma module, right? How do you prove that it's irreducible? So the way, at least I would say that, I mean, without putting a unitary form on that, I mean, that's another, actually there is another proof, but the way you will prove that, you will prove the character formula for any integrable module. And it's the same character. So, okay, so here it is. So I have, let's say, a Verma module. I'm talking about in the finite case, and more or less similar proof for the affine case. So you take the Verma module with dominant integral highest weight. Okay. Now you take some quotient here, which is integrable. And integrable means again these SL2 which integrate. Now, a priori, this may not be irreducible. We don't know that. So let's go to the irreducible quotient. Now, this is, of course, it's highest weight and it's integrable because quotient of integrable is integrable. Now, you can prove the wild character formula, exactly the same formula for any integrable highest weight module. This does not require that it should be irreducible. Now, this has the same character as this one. So this means that they have to be isomorphic. So that's one proof. The other proof is that you have to use the complete irreducibility for integrable module. And its highest weight and is completely reducible. So you could not, it's bound to be. Now, you see that proof, you have to be a little bit careful in the affine case because a priori you don't know complete reducibility a priori. So you have to be a little bit careful about that.
So what you done, it's true.
Yes, it is true. Definitely that, yeah, that there is a complete reducibility for integrable modules. But so the same proof in the affine case, you take the Verma module, you take the quotient, which I did. And if it's not irreducible, go to the further irreducible quotient. But the wild character formula or the wild cast character formula, you can prove it for any integrable highest weight module. And it's the same character formula. So it has to be irreducible. So that's the proof, at least. One proof.
Can you give a reference for disprove the well-character formula?
Yes. It is in my cosmetic book.
Ah.
So, right. Well, I mean, that's one reference. So, there I proved that, but also I think it is in Victor Casa's book, if I remember correctly. But definitely it is proved in great detail there. So. Okay, so let's move on. Anybody, any other question? Yes.
So the Weil character formula that you wrote is a reflection of what you would get if you tried to resolve this irreducible by Verma module.
Correct.
Is there a formula that you would get if you tried to resolve your irreducible by things that were given by the first construction you gave, things that are induced from dimensional?
There is. So this is called the parabolic BGG resolution, and that is available. Exactly the same one. Only difference is, I will tell you what the difference is. No, absolutely. And this is called parabolic BGG resolution. And let me see. So. So what you do, so let's take this H lambda. And so what, so let me write it F0, F1, and so on. So now here you will take Fi to be generalized Verma module, which I had the notation M hat. And now you will take W star lambda and C. So where direct sum, W should be in now W P prime and length of W is R. Okay, so let me explain that. So I am resolving this H lambda by these generalized Verma modules now. Okay, now 1 minute. I think this is the correct statement. So yeah, so let's go over this. So Fi is, now I take the minimal coset representative here in W mod WP, parabolic. So this is for general parabolic in the finite case, but exactly the same result is true in the cosmetic case.
Well, you would have affine well modulo.
Yes, that's right. So exactly. So actually, you are so right. So this is now, yeah, right. Sorry. And I take the smallest coset representative, and that will ensure that W star lambda is dominant for the finite G.
Indexed by cosets or double cosets?
No, cosets. So I'm taking a fine W, modulo finite W, and I am taking the smallest coset representative. That's important. That will ensure that this W star lambda is, of course, not dominant for the affine W, but it is dominant for the finite G. So I take the corresponding finite dimensional representation, and I take the same central charge, and then there is a resolution. Does it make sense? And in fact, there's a more general version of this for arbitrary symmetrizable Casimir case and for any parameter. Yes. Are you not so happy?
Oh, I mean, I haven't processed it, but
Yeah, okay. Okay. Yes. Okay, where are we? Yeah, so now I will prove the finite dimensionality of the space of them. Yes, so let's prove that. Yeah. So let's define so this is G tensor. I'll just write G Ti some I S plus one central element. So basically I'm taking direct sum of all these affine algebras at various points, and I've chosen one fixed parameter Ti at each point, but I take only one central charge. And the definition of bracket probably is obvious, what the definition of bracket should be. So I take X Fi, Xi Fi, direct sum that, and then let's say Yi, Gi. So this will be Xi, Yi, Fi, Gi. The central charge is basically the same as in the definition of affine, except that I just add them. And residue of dFi times Gi at 0, and I yes, times. So that's the definition. Now there is a Lie algebra homomorphism from G of sigma minus P to G hat S, which just takes XF to X tensor F at Ti and sum over I. I don't involve the central element. Now, residue theorem will imply that beta is a Lie algebra homomorphism. Okay, so once we have that, right, okay, so now the Riemann-Roch theorem implies that image of beta plus G power series Ti direct sum I from 1 to S is a finite codimension. In G hat S. So the Riemann-Roch theorem will say that image of beta plus this one is a finite codimensional test. Okay. So once you grant me that, so this requires this assumption that each irreducible component contains at least one point pi, otherwise it will not be true. Okay, so now there is this Lie algebra homomorphism from G hat at Ti I to G hat S. And what it does, that, I mean, it's the obvious one. I will call it Ci, say Zi Ci. This will go to X tensor Fi plus Zic. So I just, okay, basically I'm just saying that each Ci I'm going to map it to the same C. So see, this has its individual central element, Ci, and I'm just going to map it to the same C. So this is a Lie algebra homomorphism, clearly. Okay. So now is this lemma which I need, and this lemma, let me write it. Okay, so let A in be a subalgebra of a Gauss-Mide algebra. Okay, I'm just going to write it G hat. So I mean, such that A plus n hat has finite codimension, in G hat. Then H lambda divided by A H lambda is finite dimensional. So this is some general lemma, which let me again say, let A be a subalgebra of a Gauss-Mode algebra G hat, such that A plus n hat has finite codimension n hat. So n hat is B hat is the nil radical of correct. Then H lambda divided by 8 times H lambda is finite dimensional. For any integrable module H lambda, for any integrable highest weight module. Now its proof is fairly simple, but let me actually, this is in my book. I just write it. So once we assume this lemma, then I'm saying that the result follows, because I'll just apply it to this one, to this Lie algebra. and then the result follows immediately. So here I'm not assuming that G is simple. Semi-simple is good enough for the result. So in our case, so G hat is going to be replaced by G hat times a different Ti. So G hat. So I just apply this result to G hat Ti, direct sum of that, and just apply directly to the definition of conformal block, and we get finite dimensionality. Does that make sense?
Can you tell us the proof of the lemma?
Yes, I can. I can say the proof of the lemma. Okay. Okay, right. So first of all, so G hat is an integrable module for the adjoint representation under the adjoint. So again, I'm using the same definition of integrability that these SL2s, they decompose the representation G hat into finite dimensional sums. So that
if choose L plus 1 SL2 or having all radical one that's equivalent. So is it enough to use L plus 1 SL2?
Yes, that's right. Yes, that's right. L plus 1 SL2. That is right. Indeed, that's enough. Right. Actually, here I should be a little bit careful. Actually, what I wrote is not 100% correct. So see, I have to use a LoRa polynomial version of that. So you see, for me, G hat was G tensor C, this one, plus C. But actually, I have to use, and let me write it like that, where I have to take G tensor C first. So then this is a correct statement. Now you see, in all this, what I'm saying, there is really not too much difference because I'm taking highest weight module. So beyond a point, the power series will get cancelled in any case. So it makes no difference basically in the theory. Okay, so once we have that, then it's a correct statement that this is an integrable module with the adjoint representation. Now I'm going to write down, so given a G hat or G twiddle module, let's say I'm just going to write, actually, let me write it M right now. Define FM to be all those X in G twiddle such that and X is locally finite on G twiddle, and pi X is locally finite on M. Let's define this. So then then G twiddle is spanned by Fm. Okay.
And means as a Lie algebra. Or
No, as a vector space. So as a, no, that's the main point. It is as a vector space. Okay, so let me make sure that I'm not leaving out any assumption. Yes, so. I left out one assumption. No, I left out one define. If Fm generates G twiddle as a Lie algebra. That's the correct one. So the statement says that if this set generates G twiddle as a Lie algebra, then actually Fm spans G twiddle.
Would it be already true if you replace locally finite by locally nilpotent?
Actually, okay, so I'm not sure. So in our case, it will be for our case. But this lemma is a very general statement for any integrable Lie algebra. And what is the definition of integrable Lie algebra? That let's take vectors in the Lie algebra which are locally finite. And if that generates, okay, so right, so let me.
So it's not only the important things you want to integrate, but also something like something in the carton.
Exactly. That's right. Indeed. You see, because so I will exactly. So you see, if I take the affine Lie algebra with the derivation, now the derivation is not captured by the nilpotent elements in the bracket. So you see, but if you are going to say something is generating Lie algebra, then these should also be captured there. But these only going to act locally finitely. So if we are going to make a very general statement, then this version. But since for our G twiddle or G height, we are not including the derivation, what you say will be absolutely correct. Yeah. So definition. So any Lie algebra or a Lie algebra of any dimension, a Lie algebra S is called integrable if set of vectors X in G such that IDX is locally finite, generates X in S. So this lemma which I wrote down, works for arbitrary Lie algebra. Okay, so now let's see how does one prove this lemma. Okay, right. So
So the statement is given an integrable v theta module m.
right. No. So okay. Right. So what is the statement here? So let me. So lemma. Let S be any algebra and M any S module. Then define Fm to be this set. Then define Fm to be the set of so there's no G hat now. So there is S. And X is locally finite on S. And pi X is locally finite on M. Then G, okay. Then S is defined by Fm as a vector space if Fm generates S hat as a algebra. Okay, so this is now the statement I want to say. Completely general. Yeah, that's it. That is the statement. So is the statement clear? And now I'm going to use this lemma to prove this one. Yes. So I'm going to use this lemma to prove this one now. So let's prove that. Okay, so let's prove this. So now I just have to apply that to the proof goes by so I want to say that now I'm going to take G divided by A plus N. And by assumption, this is finite codimensional. So this is finite dimensional space. So this will be spanned by some vectors x1, xn. Span. So this is span, not the Lie algebra, span. And xi act locally finitely. On H0 by the last lemma.
X are representative in V hat of infinity coefficient.
Say it again.
De XI yang representative in V hat.
Yeah, in the quotient, in the yeah, sorry.
They are not in the groove.
No.
They are in V hat.
Yes, yes, right. So they're not in the quotient, right? Yes, now this is yes. So there is a subspace is defined by x1 through xn in G hat, such that xi acts locally finitely on h lambda, and this adds up to whole G hat. Right. Okay. So once we have that, then I'm saying that this action now can be broken. So this is space now we have to consider h lambda. So h lambda yes. So now we take h lambda and divide by what is the notation I used? By a lambda. Yes, a lambda. Okay, so I can write this as okay.
So it takes I act locally finitely on H, but also on V.
Yes, that's right. That's right. As well as RG. That's right. That's right. Yes. No, we will need that. So now I want to say, so this is space we want to say that this is finite dimensional. So okay. Let's see. So actually, I want to say that h lambda by n hat, h lambda what do I want to say? Okay, so this one is a plus n hat plus x1 xn on the highest weight vector here.
You mean to some universal enveloping?
Actually, I don't even need that. This, right?
But is there a universal? I can't see.
So I'm saying that h lambda, I can write it as a plus, this is space, acting on b plus.
Some sort of, yeah, okay.
Right.
Which means all,
Yes.
that's, yeah.
Yes.
Because that's not a Lie sum.
Yeah, it's not a list of algebra, but you take all the operators like that.
Good.
Correct. And you are operating on that. So you see this cancels, so this remains. operators on x1, xn acting on V plus. So this is operators now, sorry. Okay. So that's what it does. Now, but these are acting locally finitely on that. So this will be a finite space.
Actually, is that totally clear if they don't commute? Did they individually load?
You see, because, okay, I can apply x1 to V plus, I mean to the power, whatever power I want.
Oh, yes, okay, sorry. Like, you can use them in a specified order. Yeah, okay.
See, the way I would do, yeah, right.
One specific order.
He's using some, you're using some sort of Poincare-Berkoff width somewhere, right?
Yes, yes, yes. That's right. I am definitely using Poincare-Berkoff width because I'm right.
You don't have the bracket of x's. For Poincare-Berkoff width, you would need. You can exchange x1, x2 to x2, x1 if you already have the bracket of x1, x2.
But that's also locally finite.
Why?
Because see, so these xi are acting on g hat also locally finitely.
But doesn't Poincare-Berkoff width say you can express everything in U of G as a product U of A times a product of these in specified order times U of
Exactly. That's what I'm using. That after all, yeah, I am using that. I will first apply n hat, which doesn't do anything. Then I will apply x1, x, or then I will apply A, and then then I will apply x1, xn in any specified order. And what remains is only A action.
U of A, yeah.
So I hope I am saying it correctly. Yeah, I did not look at the proof before coming here, so I'm a little bit struggling, but I think that's the idea. So that's that.
Wait, did
Yes.
you not use the second lemma?
No, I used the lemma.
Or did you use the second?
You mean this lemma?
Yeah.
See, I used because, see, so first of all,
I used it to know that these xi's were individually locally finite.
span. So first of all, they span. And secondly, they are locally finite. So I used two places that they span and they are locally finite. Because otherwise I could not have extracted a finite dimensional space. So I use this lemma. And actually, this lemma is not difficult to prove. I mean, this lemma is very, in fact, I've written all the hypotheses, so I think I've stated the lemma correctly. And this is not difficult to prove. Again, I mean, it's in Casa's book as well as my book. So
can you tell where to look?
Right. Okay. Right, that's right. Yes. Okay. So right, I will tell you. Yes. Okay, really. Okay, how about, I don't have that here, but actually this is in my Verlinde book, but it's before that. I mean, it's also in Casa's book. I don't remember the reference for that. So Yeah,
But in our case, could we do what Pierre said and produce some use nilp elements that act locally nilpotently, or it's not enough? Okay, you already said it's not enough.
no, nilpotent element will not be enough. Right, that's right, that's right. Yeah, so, okay. So please don't take this as that I'm trying to advertise my book. Please don't take it that way. But I'm going to send a copy of my book to all of you, an electronic copy, and I will also point out the reference there. And I will also, at some point, I will get the Verlinde book and I will give it to you. But please don't take it as I'm trying to advertise. No, I'm not trying to do that. So then I will point out the precise reference. It's in chapter 1 somewhere, but I don't remember the reference. Unfortunately, I have not written the reference here. Okay, so let's see. So I think we have proved these two results, that this space of conformal block is finite dimensional and it does not depend upon the choice of the local parameter. So next time, I will do the propagation of Vacuum and factorization theorem. I will give an indication. I mean, the full proof is a little bit long for both of those, but I think I will give you enough idea as to what the main ideas behind where the proofs are. And then, so that will be the next lecture, and following lecture, I will do the deformation, so invariance. So that's the plan. So I hope to, in 4 lectures, more or less wrap up the Lie algebra part, and then do the group part where I will connect it with the moduli of vector bundles or G bundles and sections there of certain line bundles there, and identify that with these conformal blocks. So actually, I forget, next week, I think there is no lecture. I forget now.
Because it's the special year workshop, is that right?
Something like that, yes.
Okay.
Something like that. That's what one of the secretaries told me, that next week I can't have my lecture.
Well, if depending on, we could find another room for it.
Okay.
But maybe we should see if people want, anyone is going to go to the special year thing. Actually, I might go to that.
Oh,
But it's up to you. We can find you another room. I don't think that would be a problem.
I'm fine with
I
that.
think we want you to be.
Okay.
No, but we don't want you, exactly. So you said you want to go to that.
Yeah.
No, then let's not do that. So yeah, in November, I think I have at least 4 lectures, and December 1st, 1 lecture, 5 lectures. So at least I should be able to give a good general idea of the whole theory. So I think I will start here unless anybody.